Hello, everybody. This is Dr. Flight. I hope you are all doing great. I want to walk through just a couple highlights when it comes to MANOVA and the assumptions that need to be considered as you move forward in performing a MANOVA. So if you're familiar with a MANOVA, then you'll know that it distinguishes itself from an ANOVA because we use multiple dependent variables. So in other words, what we're creating here is a variate based on dependent variables for each independent variable level that we have. So if we have a grouping variable and there are multiple levels in the grouping variable or multiple groups, then we're using our, in this case, dependent variables to create a formula or a weighted variate that describes each of the groups based on those dependent variables. Now remember, MANOVAs swap around terms a little bit. So a dependent variable in this case will be a metric or a continuous variable ratio or interval level variable, and we'll use more than one. So we'll have at least two or more of these that we'll use. This is different again from an ANOVA because typically we would only have one dependent variable in that particular case, but a MANOVA uses multiple dependent metric variables. And then we need, of course, one at least non-metric independent variable with at least two levels. So you can have more than one for sure, but you have to have at least one. So these again are things that we need to see. Observations need to be what we call independent. So dependence between observations would not be something that we can have, and we're going to assume or make some testing hypotheses that groups are different in a certain way, but observations, respondents need to be independent of each other. Sample size needs to be sufficient. So if we have multiple groups, then each group has to have a sufficient number within it. So 20 or more respondents in each group would be what we would like. There's also this caveat, at least the number of levels times the number of dependent variables, but really we want to shoot for a robust number. So if you have two or if you have three levels in an independent variable, then you need at least 60, a sample of 60 with 20 in each. And ideally, we also want to have a similar number in each. However, that's not required. So in other words, you don't have to have the exact same number in each group or each level of independent variable in this case, but you want it to be fairly similar. Then homogeneity of the covariance matrices is something that we want. So this is actually important. It'll be tested within the process of doing a MANOVA. But basically what we're saying is the variance of the error terms should be equal or near equal, similar across groups. So if you have a treatment for a test where you have maybe distribution channels, you have 3 different distribution channels that you're testing, the respondents, the variance of the data of the dependent variable, the variance of the dependent variable should be similar across all 3 of the distribution channel respondents. So they should be homogeneous and not heterogeneous. So homogeneity of covariance matrices is what we're talking about there. Other things that we want to look at, recall we have normality. So normality is an issue. We can check normality again with the dependent or the dependent variables. I happen to say dependence list here. This is an explore. You can also make sure you check for this through other methods in SPSS, but we want to run the normality tests for the dependent variables. Remember, with MANOVA, our independent variables are non-metric, so obviously we wouldn't be checking this because well, they don't follow normal distributions, so it wouldn't make sense. So normality is important. We've got the Shapiro-Wilk test that we can certainly test for that. Remember, the null hypothesis here is that you want something above 0.05 for the Shapiro-Wilk test. And that is an acceptable test then for normality. You can also look at histograms. You can also look at standard deviation, the moments, kurtosis, and skewness statistics, and see where they are relative to a normal distribution. Make sure that makes sense. Okay, so again, we've got significance going on here because they're above 0.05. So this is again flip-flopped from what you might normally do, but that's how you interpret that test. Linearity among these variables, so linear relationship between each dependent variable within each of the independence groups is what we would look at. For this particular, for this particular test of linearity, normality, these are all things that are pretty typical. If you want to do this, I'm not sure. We've done this with probably metric variables, not metric, but metric variables. We go to graphs, then legacy dialog, scatter dot, matrix scatter. So matrix variables as matrix, that's what that should be. Sorry about that. Got a little misprint there with the X anyways. We have, in this case, a distribution system, so that would be the independent variable in this example, and then we have 3 continuous variables. And what that yields is going to be these types of boxes where we're looking for linearity, and we have 2 different. We have the 2 different distribution systems: indirect, which is here, and then direct here, and then we have 3 different variables, and we're looking at between each combination here. So we have these combinations with X19 and X20 and X21, and we're basically looking for linear or straight patterns of data. So linear relationships between each of the dependent variables. In this case, we have X19, 20, and 21 for each of the independent variable levels. We have 1 independent variable distribution system, and there are 2 levels of distribution systems. So that's why we have so many things here. And again, we have this matrix right there, just kind of restating what we did before. Note here that we're observing the oval or cluster shape, and what we want to make sure is that it's not like a round circle, but that there's a pattern of some type of linear suggesting relationship going on. Okay, so this is the assumption of linearity. Multicollinearity is another issue that we look at. So again, we want variables in this case to collinear sum, but it doesn't need to be too obnoxiously high. So greater than 8 or 9 is an obnoxiously high correlation, but we do want variables to correlate some or expect them to. So while these seem high, they're not over the bounds of being too high. Much more though than we would probably be a little bit concerned with what's going on. Finally, and again, heteroscedasticity is something that we'll look at later on when we're actually running some analyses. But moving on to this final area, we would think about outliers. So like several of our different analyses, the estimation of the variance may be subject to extreme values that are identified by outliers. So following along, running a regression, but using as the save variable within the save variable. So it should be right here under the save, we'll have Mahalanobis distance, and then you can follow along and remember that we want to take the number of variables in this particular case. We have 3 variables that we're running this off of because these are the ones that are going to be built into our ANOVA. But we're running this so 3 times probably 2.5, and if it's a larger sample, you can go up to 3 or 4 even if you want. But a conservative number would be a smaller number, so 2.5 might be something that would be appropriate. And then what we do is within our data, after we run Mahalanobis distance squared, we look and see how many exceed that value. So if we had a cutoff again of 2.5 times the number of variables that we're looking at, in this case 3, 7.5 would be the cutoff. And what it's saying is that we have this one respondent here who seems to answer in an abnormal way, unlike the other respondents, dramatically unlike the other respondents. So in that case, we could choose to eliminate that particular respondent from the analysis and then move forward from there. Okay, so the basic assumptions then, we're talking about linearity, we're talking about normality of data. We're concerned with what we just saw here in the outliers. We're very concerned with heteroscedasticity, which we'll look at moving forward. And then we talked here also finally about multicolinearity, and where we look at a correlation matrix and just simply look at the R values there, and that should give you enough of a heads up to see whether we're sufficient or not on that. Okay, so again, this is just a quick review of assumptions for MANOVA, and these are assumptions that we often run on our data no matter what, but when we're adopting new methods or techniques, we want to review the assumptions that would be germane to that particular method that we're using. So that's what these are for. Okay, so great. If you have any questions, let me know, but this would be the assumptions then that we follow for MANOVA.